Hi, my name is Petr Andriska, and it's my pleasure to tell you about the collaborative augmented reality on smartphones powered by city-scale visual maps. This work was developed at Blue Vision Labs, the company I started and that was acquired in 2018. Much of today's available augmented reality is still a single user experience. For example, in games such as Pokemon Go, you can see and interact with the content, but your friend does not see the same content at the same place. This is because the fundamental piece of technology, the backend map that would join all these experiences together, is missing. Our work presented today is very much about how to build this map at scale and how to use it to power such augmented reality experiences. Before we begin, let's start with a quick demo of the resulting system. Everything in this video is real, without any post-processing. I hope you enjoyed the video and can see that the system is very powerful and can be used to build many exciting experiences in gaming, navigation, and others. Let me tell you how it works. The system consists from multiple steps. First, a map of the city is built from a collection of images. Because this map is very big, it has to live in the cloud. The map houses precise position of various augmented reality content that users can see and interact with. Localization service that allows real-time centimeter accuracy localization on several smartphones at the same time over the network. Finally, knowing its position, devices can see augmented reality content and other users properly positioned in the real world. Whereas there has been several works before that studied individual components, we are the first ones that built and study the entire system end-to-end. In particular, we present novel solutions to 3 problems that are key for a smooth production performance. How to build map at scale, how to localize over the network, and how to solve various failure cases. Let's first talk about map building. This is done by first collecting data at scale using camera-equipped vehicles in the area, and then computing a large-scale structure from motion 3D map of the city using the cluster of computers. We collect data to build 3D model of the city using vehicles equipped by cheap camera rigs. This can be done efficiently in a matter of few days for an average city. and this process results in billions of images with GPS tags. Next, we use large-scale structure from motion to compute the 3D map from this data. As the known algorithms don't perform at this scale, we use hierarchical structure from motion. First, we split the data into overlapping clusters that are computed independently. The redundancy is important and a key to being able to construct the entire map, even in the case if several subcomponents are missing due to various data problems. The resulting computation takes 90 hours on a cluster of computers, but because of its horizontal scalability, it can be significantly speeded up by employing more computers. The final map can be visualized in a form of point cloud, as shown here. It contains billions of points capturing the structure of the city. It can be also overlaid on top of existing 2D maps, where you can see the map aligning with existing structures such as buildings. Next, let's talk about localization in this map. As said before, the map is very large, and because of this, it has to live in the cloud. To allow real-time localization, every smartphone is running its own visual odometry system that is being synchronized with this map. This synchronization consists of computing transformation between local and map coordinate system. It is done by sending pictures to the cloud to determine their position in the global map. And from the knowledge of their both local and map coordinates, the resulting transformation can be computed. Here you can see two users using the system that are being localized in this map. Localization is very accurate, resulting in the ability to see each other's location on the screen thanks to the ability of both devices to localize in the same map. You can see both devices are walking through the map and being able to interact with each other. Here you can see comparison between localization accuracy of the proposed visual localization in blue and GPS in red when walking down the street. The visual positioning system is significantly more accurate than GPS, and this is necessary for smooth augmented reality experience. We also observed that the performance of the system improves just by collecting more data to build the map. This creates a simple procedure. If you want to improve the performance of the system, we just need to collect more data to build the map. Let's look again at some of the experiences possible to be built using the proposed system. Collaborative gaming, where everyone sees the same thing and can interact with the environment and with each other. 3D tagging of the content on the street to be left for others to discover. Intuitive augmented reality navigation, where you just follow the arrows to get to the destination. At the bottom, you can see the difference between visual positioning system in green and GPS in blue. The system also works on vehicles equipped by phone or a camera, and where it can provide high-precision localization and instructions about the path, tag traffic lights, traffic signs, and other information stored in the map. Finally, when we can localize both pedestrians and vehicles, you can create experiences as this one, when you can find your taxi on a busy street just by looking around. We believe having ubiquitous augmented reality is the next step in the development of the field, but it requires powerful infrastructure in form of city-scale maps. And as you could see, these systems can be built efficiently at scale and to power many exciting applications already today. We think this is the next exciting step in a new era where people and hardware can interact with the environment and with each other in completely new ways.